Okay, so welcome back. It's been a long break. We haven't seen each other in 2 weeks. So today the plan is I'm going to talk about the solution of assignment 3. I've graded your third assignments and the grades are posted on the news group. And after that we are going to finish talking about the randomized incremental algorithm to solve these two-dimensional linear program, which was the goal was the casting problem. Find the direction that satisfies all these constraints, find the direction which makes at least 180 degrees for all mold faces, if you remember that problem. So we are going to finish that problem by discussing this incremental solution and the randomized incremental solution, the worst case running time complexity of O(n) square, and we are going to see the expected running time is linear. And we are going to also see that the similar approach, the randomized and incremental solution, these incremental solutions are fairly easy to implement compared to other techniques like the plane sweep, for example. It's easier than plane sweep. These incremental algorithms are easier to implement. The algorithms are very simple. And also, their expected running time is linear. So it's really good. I mean, it's easy to implement. And also, they are fast. So we are going to talk about another problem, the smallest enclosing disk problem. So given a set, that problem is given a set of points, what is the smallest disk that encapsulates, that encloses all of these points? Can you find the smallest disk? And it has such a problem has many applications. For example, imagine you want to know where to place a robot arm, and the robot arm, for example, has to reach to a number of places around it. So what is the best place to place the base of the robot arm so that it can reach imagine it can turn 360 degrees, but I mean it cannot, you don't want it to translate on this plane. So you want to fix it on a table and you want it to be able to reach everywhere around it, every object that it needs to interact with around it. So it's the base of this robot arm actually corresponds to the center of the circle that encapsulates the center of the smallest circle or disk that encloses all these objects around the robot arm. So there are, we can think about other applications as well. And we are going to see another incremental approach, an incremental algorithm that we are going to use to solve this problem also is going to have an expected running time of O(n). So the naive solution has a solution of O(n) to the 4. So you reduce from O(n) to the 4 to O(n) with just a simple algorithm, randomized incremental algorithm. And the other thing, I mean, the best known solution that doesn't use this randomized incremental approach is O(n) log n, which uses Voronoi diagrams to solve the same problem. But we are going to see a very similar approach to this half-plane intersection problem can be also used to solve the smallest enclosing disk problem. So we are going to, after we finish this, this is going to conclude chapter 4. And we are going to start chapter 5, which is orthogonal range searching today. And we are going to see two data structures, which maybe you may have seen them in courses like multimedia databases, or I mean, probably in databases you have seen these data structures, but for those who haven't seen them before, we are going to see today KD trees and range trees. KD trees and range trees, they allow orthogonal range queries, meaning that if you, and in multi-dimensions. KD trees and range trees, both of them are, they scale to higher dimensions, but we are going to see their examples in 2D. So our goal will be given a two-dimensional set of points. This may be your database, your coordinates. There's a bunch of points, like 1 million such points, and your goal is to find all the points that fall within a query rectangle. In other words, this is an orthogonal range searching. So you're wondering whether which points have coordinates between this x and this x coordinate and this y and a particular specific to y coordinate. So you are going to have a query window, and your goal is to find the points that fall into this query window in a short amount of time. Of course, in linear time you can do this. You don't need any data structures. You can check every point whether it's in this rectangle or not easily, right? I mean, it's very easy. Just look at a point. Does it have x coordinates between these values, and does it have y coordinates between these values? If so, then it's in the rectangle. You can do this check for all the points, but usually in databases, the queries which take O(n) time, where n is the number of items in your database, is a very bad performance. So to answer such queries, you need to go over all your database each time. If imagine you are performing such queries often, I mean too many such queries, and this O(n) time is going to be a very big bottleneck if you are performing queries frequently. So our goal is to reduce this query time to smaller numbers, and KD trees allow us to reduce this to square root of n plus k. Of course, these such range queries are also output sensitive. If your query rectangle is very large and it encapsulates all the points in your set, then you cannot do better than O(n), right? I mean, if you are going to report all the points in your database, then you need to go through all the points. So again, this is an output sensitive algorithm. But if your query rectangle is small, I mean, if this k is small, you don't need to go through all the points. In KD trees, the square root of n is the time complexity of the KD trees, and range trees are going to allow us to do this query in log square n time. So it's going to reduce the time. So log square n is smaller than log n times log n is smaller than square root of n. But it's going to come with, so this is time with in space O n log n. So it's going to build a data structure which has this complexity, but KD trees, the space complexity is O(n). Okay, so depending on whether you want more, I mean, you have space limitations or not. If you have space limitations, space is more important to you than running time, then you can use KD trees. Otherwise, range trees are going to provide faster queries, but at the cost of an increased amount of space. For example, and this increase may be, I mean, this n log n may be close to n, but imagine, for example, this log n is 10, okay? So it's 10 to the 10. Imagine your database contains 10 to the 10 points. So 10 billion points, okay? If it means that your database is now the index that you store in your database is 10 times larger than the original database size. So if the original database was requiring 1 terabytes of this space, you need 10 terabytes to store this range tree index structure. But if you use KD trees, again, 1 terabytes or 2 terabytes would be enough. Okay, so this is this n log n, and the difference between n log n and n can sometimes be significant. So this is what I'm trying to tell. Okay, so we are going to see the details of all these things today. Now, let's go back and let's start with the homework. Most of you got full credit from the homework 3. Let me remind you what that homework was, because it's been, I think, more than it's been 3 weeks since you have done this, you have submitted this homework. So it was asking whether it's possible to traverse all the incident edges of a vertex for which that vertex is their origin by making repetitive calls to next twin, next twin, next twin. Okay, so the first one is the incident edge. You get the first incident edge. It may be an arbitrary edge, and taking the twin of this and the next of this, and taking the twin of the other one and next of it. So repetitive calls to these next twin. Is it possible to traverse all the edges, all the incident edges, and whether this traversal has a certain direction? Is it always clockwise or counterclockwise? So this was the question. And most of the proofs are proof by induction. First, in a base case, you showed that, you show, for example, if you have 3 incident vertices, these 3 incident vertices are traversed. By the way, I also remember in certain cases we need an additional assumption so that we are able to traverse all the edges. For example, if the vertex is incident to the unbounded face, in other words, for example, let's review this again. So this is our vertex. So this is our vertex here, and it is incident to some edges. And here we assume that there are faces here. Face 1, for example. Face 2 and face 3. Okay, so this is this way, this is this way. Okay, so, and this is my vertex. So in this base case, you can see that if starting from an arbitrary incident edge, for example, starting from this E11, let's say it E11. So E11's, by the way, one important thing in doubly connected edgeless is that the next of an edge is always unique. Okay, so this is very important. Because if the next of an edge is not unique, then you run into problems. Which one are you going to pick? So the next of an edge is unique in such a way that, because the reason is that an edge and a half edge bounds a unique face, and the face this half edge bounds lies to the left of this. By construction, by definition, each half edge bounds the face that is to the left of it, okay, locally. So this is by, you could have defined it the other way. I mean, this is by definition in the book. I mean, this is not some universal fact. I mean, you just choose to construct your data structure in such a way. You could have chosen the otherwise, but according to this definition, so and therefore, according to this definition, the outer boundary of each face is in counterclockwise order. So the next of the twin of E11 is this, and the next of E11, for example, when you come to here, okay. So this is the face. This is one half edge. This is the other half edge. Let's name, for example, E33, and this is E22. Okay. So when you come to this twin E11, so this is twin E11. The next of twin E11 could be E33 and E22, right? I mean, both of them could be the next. We are here. The next, an edge that follows here could be E33, but the next of E11's twin cannot be E33 because E33 is bounding a different face. Okay, the next of twin E11 should bound the same face. Okay, because the purpose of having the next pointers is that to go through the edges on the same face. If the next pointer takes us to another face, then it's not doing its purpose. So the next pointers therefore are unique and they're bounding the same face. So the next of twin E11 is E22, and the next of the twins E22's twin is this one. Its next is E33, and similar we go back to E11. So for this base case, we traverse all of the incident edges, and they are traversed in clockwise order. So it's true for base case, and you assume if it's true for vertex with n incident edges if it's true. What will happen if this vertex has an n+1, n+1st edge that is inserted anywhere, and this insertion can be in the middle, but without loss of generality, you can assume that this insertion is at the end of the vertices because the incident edge arbitrarily can be selected to start from anywhere. So therefore the insertion, even if it's in the middle, if you select the incident edge to be the one just before it, it's going to seem like the new added edge is going to be added to the last of this ON, and you draw the same figure and see that the new inserted edge. Again, in order to prove this, you need to use the geometry, the definition of the doubly connected edge list. I mean, without discussing the geometry, seeing that Twin is bounding this face and the next is should be on the same face. Without discussing the geometry, it's not possible to prove this. I mean, and some of the proofs, they also got full credit. You don't even need actually proof by induction. By just discussing the geometry of this construction, the definition, by the definition of this doubly connected edge list, the Twin and next of the Twin should be the face to in the clockwise order. So by just even discussing the geometry, you can convince me or other readers that this is going to give you clockwise traversal around the vertex. However, the thing is, the problem here in cases where here this was an example that we discussed. If the same face appears in here, for example, and in here, and such a case can happen if that face is the unbounded face. For example, look at this. Our vertex is this. I have a face here, and I have another face here. Okay, so let's see whether it's going to be a problem. So this is V. So this is counterclockwise order. It's the outer boundary of phase 1, phase 2. So these edges are outer boundaries of phase 1, and this counterclockwise, this one, is the outer boundary of phase 2. Now, and this is the unbounded face. Okay, it's everywhere. The unbounded face is here. So these F1 and F2 are like holes for the unbounded face. So they also bound. So for example, this twin edge, let's say now this is E11. The twin of E11 is bounding FU. Okay, it's a hole in FU. But you are going to see when we come to this here, okay, so we have this one again bounding FU, and we have this one again bounding FU. Now, the problem here is that since both this one, let me use a different color for them. Okay, the problem is, what is the next of twin E11? Okay, it could be one of those yellow half edges. Which one is it? It's because since these yellow edges are bounding the same face, it's the unbounded face, so here actually we see a problem with the doubly connected edgeless definition. The next E is not, the next of this one could be this as well. Why? Because it's also bounding FU. Because you may be traversing this all. The thing is, are you going to, these two holes that touch each other at this vertex, are you going to consider them as a single hole by traversing them like this? Or are they going to be double holes if two different cycles? So is there a single cycle here that goes to, the problem is that cycle is like, is shrinked at this vertex V. So is it a single cycle or two cycles of holes? So that's the problem. If we, in order for, maybe we can add this definition, add this thing to the definition of doubly connected edgeless, if such cases occurs, if two holes touch each other at a vertex, we consider them as a single hole, and this becomes if this becomes a single hole boundary, if we say that, then we solve this problem. Okay, I mean this problem can be solved actually by doing this assumption. If two holes touch each other, there's considered as a single hole, and there's a single hole boundary, inner boundary cycle around them. Yes.
I think this is a single hole because we have only one vertex at the connecting point. I mean, if this were two holes, we should have two vertices.
Oh, two vertices at the same point.
Same point. So,
yeah, it's a single hole. Yeah, it's a single hole, but it's like not a simple polygon. I mean, because it's sharing I mean, some kind of a degenerate hole in a way. I mean, but that's also a good point. I mean, if it's the same vertex that here it should be considered as a single hole. So if you consider it as a single hole, then there's the single unique. So the next, if in such a case, the next of twin E11 should be this. Okay. So if you need some assumptions in our definition, in our construction, to make this next unique. Okay, and this one is going to make this unique. Yes. If it's a single hole, yeah, that's another good point. Single hole, now there are two, F1 and F2 are two faces, okay? So then, I mean, this contradicts with our definition with single hole. So it's a single hole composed of two faces. So it's also, I mean, it's not very easy to determine. So it's a composite hole. This is a new definition to the doubly connected edgeless, and hole can be composed of multiple faces. And this happens, I mean, because this is a degenerate case. It's an extreme case, but just discussing these points, we can see the shortcomings of the double connected edges, or the points that are not discussed in the book. Okay, so we need to handle such degenerate cases by making additional assumptions. Okay, so this was the homework. I mean, again, as I said, most of the solutions were proved by induction or discussing the geometry of the construction process, or a property. By using the properties of the doubly connected edgeless, you can directly prove that if all the faces are bounded faces around it, this holds true, meaning that you are able to traverse all the incident edges and in a clockwise order. Okay, any questions or any points that you want to share? All right, so let's get back to the problem of the linear program, the two-dimensional linear program that we were trying to solve. And we haven't, so in this chapter, we are actually we are skipping some sections, so you are not going to be responsible from those sections in the midterm. So today I'm going to list the subsections that you are responsible for the midterm. By the way, let's start talking about the midterm. Let's start discussing about the midterm. So we are going to have our midterm next week here in this room at the same time. So just come as if you are coming to class, but don't forget to study. And the type of questions are going to be similar to exercises at the end of each chapter in the book. So similar to homeworks, but it's not going to take as much time as homework. So some questions may be simpler than others. There may be a couple of difficult questions, but if you look at the exercises, if you want to practice for the midterm, you can look at the exercises at the end of each chapter. So the questions are going to be similar to those exercises. And it's going to be probably at most a 2-hour exam. I'm planning like 1.5 hours, maybe a short midterm as well. So probably 3 or 4 questions at most. This is a good question. I haven't thought about it. Maybe open book. Okay, it's maybe open book. So I don't see why it's not open book. So it's maybe open book. So you don't need to memorize these theorems or other things. So I think it's. I'm going to make it open book. So it's going to be open book. So for those who don't have any copy of the book, this may be a problem. So I need to think about it as well. I mean, if the technology, I mean, you may have some e-readers, electronic readers, but the problem is that e-readers, they may access everything other than the book. So that's a problem. How can I have the e-books only access to the textbook? Let's see. I'm going to. For one of you who don't have the book, I can provide my copy, but. Let's see, maybe if you want, you can take my copy today and just Xerox copy the first 4 chapters for studying. Okay, you can also do that if you don't have a copy of the book. Okay? Oh, okay. Okay, so I mean, you can also get it from our copying center. All right, so. Let's remember the problem. Any other questions from about the midterm? Okay, so let's get back to the problem. If you remember the problem, we were trying to find the intersection of half planes, which was going to be our feasible region for our direction. So our solution space was the xy plane. So we were trying to find xyz extraction vector. So this is our mold. So our mold has some object in it. So for example, something like that. It may be infeasible to get it out. And our goal is to find a direction to pull this object out of this mold by a single translation. And after studying the geometry of the problem, we have seen that each mold face, phase 1, phase 2, phase 3, phase 4, phase 5, phase 6, each mold face defines a constraint for us in terms of the pulling out direction. For example, this F6, the pulling direction, if this is the normal, inner normal of this phase 6, the pulling out direction should make at least 90 degrees with this normal vector. Okay, it can be the smaller angle that it's going to make. It can be any of these directions. But if it's in this direction, we will not be able to. This face is going to prevent to pull in a direction that from this. So it's like this direction gives us a half plane that is the feasible region. So if we write this angle between the pulling out direction and the normal of this face, we see that what we get ourselves is a linear constraint. The linear constraint is of the form if the normal of that face is nx, ny, and z. So what we have here, without loss of generality, we can assume we are on the z is equal to 1 plane. So z is equal to 1. The pulling direction changes. We are only looking for different xy directions. We are looking for an xy vector plus 1 is less than or equal to 0. Okay, greater than 90 degree. This is the dot product, which gives the cosine of the angle. So the dot product between two vectors give us the cosine of the angle, and being greater than 90 degrees means that the cosine of that angle is negative. So this gives us, since all these normals are known, and this is for one face, and we have, for example, if we have 6 faces, we are going to have 6 such constraints. So this is the nx1, this is the normal of one face, normal of the other face is going to give us another constraint, and z2. So we are going to have 6 such constraints for this mold. And our goal is to find an xy value, an xy direction that satisfies all these constraints at the same time. This turns out to be the problem of, so each of these constraints, since they are linear, they define such a constraint. This becomes a line on the solution space. This nx plus 1, nxx plus nyy plus nz defines a line on the xy plane, and everything that is smaller than 0 defines a half plane. So in our solution space, this is going to be, if this is our solution space, one of these constraints is going to be a line like this. So it's going to be a line like this, and depending on depending on whether it's less than 0 or greater than 0, we are going to have a certain region that is feasible. So this part is the infeasible part. So this line is going to divide the whole plane into 2 regions, where one direction, the xy values are infeasible, are not valid, does not satisfy the constraints, and the ones that are left of this line satisfy the constraints. So our goal, in order to satisfy all of the constraints, this problem turns out to be the intersection of these half planes. So if there's another half plane which says that this region is the feasible region, then the intersection of these 2 is going to be here. And each time, our goal would be to find the intersection of these 6 half planes. And we see that these intersection is always going to be a convex region. The intersection of these lines, the half planes, is going to be convex. And another important property that we observe here is that when we add new half planes, since we are computing the intersection of these half planes, this region is monotonically non-increasing. Okay? I don't say it's always decreasing, because for a certain half plane, for example, if it's in a region which is also, some half planes may already include this region in it. For example, look at this. If I have another half plane and the feasible region is this one, okay? In that case, the intersection of these 3 of them does not change. This new added half plane does not change the intersection. So it's not always decreasing, but I can guarantee that it's never going to increase, because I'm finding the intersection of these half planes. The intersected region, when I'm adding new half planes to this intersection, the current region does not increase. I always add new constraints. It can decrease. It's going to get smaller and smaller. At some point, it can get to 0, meaning that there's no solution that satisfies all these constraints. So there can be 2 different things, whether there's a feasible region or there's no feasible region. Actually, we are going to see 4 cases regarding our solution when we convert this to a linear program. But we are going to use this property of the monotonically non-increasing property is going to be used in our incremental solution. Here, and the intersection of half planes by using the algorithm that intersects convex polygon can be found in O n log n time. So if we have an algorithm that, and we haven't covered this algorithm in detail, so you are not going to be responsible from this intersection of convex polygons section, you are not going to be responsible from this. From this section, the only solution that you are going to be responsible for is this randomized incremental solution. And this the n log n solution intersects convex polygons each time, and it's a recursive solution. You find the intersection of the first half of the half planes, you find the intersection of the second half of the half planes. What you get is two convex regions. You intersect these two convex regions to find the overall solution. So the one that uses intersection of convex polygons as a procedure, as a solution in its solution, uses a recursive solution. Means that, I mean, if you know how to find the intersection of two convex regions, what you can do is intersect the first n over 2 half planes and intersect the last n over 2 half planes and merge the result. And merging the result is, again, intersection of the two results, because you know the results are going to be convex regions, and you intersect these two convex regions to merge. So this gives an n log n solution. It's very similar to merge sort. It's the complexity is Tn is equal to, so this is the recurrence relation. And actually we have plus n. This n is needed because we need to be able to find the intersection of two convex polygons in O(n) time. Okay? And this leads to the n log n complexity. Yes?
The previous inequalities for the normal vectors, why is the inequality in the second one is smaller than 1?
Oh, no. It's a typo. It's always less than 0. Okay? The constraints are the same for the all half planes. So it's just a typo. Okay, so this solution was O(n) log n. And the next question that the solution now we are going to think about is, do we really, can we decrease this even more? Can I find this feasible solution, xy, in linear time, for example? And we are going to see an algorithm which promises an expected linear time solution. And this comes from the observation that if we are looking for a single direction, a single direction that satisfies all these constraints is enough for us. But the solution that uses the intersection of half planes actually gives you all the possible solutions. At the end, it gives you the feasible region. And any direction from this region is a valid solution. If we do not need all the valid solution, if all we are looking for is a single valid solution, we can convert this problem to a linear program. And that linear program can be solved in expected linear time. So this is the next thing we are going to do. We are going to, instead of maintaining the intersection, the whole intersection, we are not going to maintain the whole intersection each time. All we are going to maintain is a certain extreme point within this intersected region. So we are going to maintain a single vertex of this feasible region. We are not going to maintain any other thing. Okay, so just a single vertex at each time that we know is a vertex of this feasible region, and we are going to provide an incremental solution each time. Either we are going to update this extreme vertex or not. Based on, we are going to add these new half planes one by one and see how this vertex changes. And the solution is based on it. But first, before thinking about this vertex, how do we choose this vertex? So, if you're in this region, which vertex are you going to choose and are you going to maintain? So you cannot change this. What is the strategy to change this vertex? To have a linear program, the way to choose this single vertex is with what we call an objective function. In a linear program, in addition to these constraints, so in the original program, all we have are these constraints. Okay? We just need a point that satisfies these constraints. But in a linear program, we usually want to maximize or minimize something, an objective function. So for example, out of all the xy's that satisfies this, so you may have a list of xy's, directions, out of all these directions that satisfies these 6 constraints, if many of them satisfy these constraints, which one do you prefer most? Okay, so this is your objective function, the one that you prefer, and you can write it as a something like this, C1 plus, like you can, these x and y's, again this objective function is usually, I mean in a linear program, your objective function is also a linear function. It's a linear term, it contains linear terms, and you can either maximize this or minimize it, okay? And here in our case, if our problem does not impose anything about, I mean, if your problem just says that, just pick, you can pick, you're free to pick any of these xy's, okay? If your program just, if your problem just says that you can pick any of these, it means that you can just pick an arbitrary objective function. So just max, for example, you can say maximize x plus y. Okay, or minimize x plus y. It doesn't matter if the problem that you're dealing with does not care about how these xy's look like. But in a general linear program, your problem tells you. The problem tells you, for example, maximize a profit. Okay, minimize a certain cost. Usually in optimization problems, this is what we are looking for, a solution, and out of possible solutions, we are looking for a one that maximizes something. For example, there may be some items that you are going to store in a ship. You are going to transport these items with the ship to somewhere, and for example, the constraints may be whether these items fit in the ship or not. So this is a knapsack problem. Now, any selection of items, that, I mean, you can select one item and it's going to fit in the ship, okay? But here you are trying to maybe, for example, maximize your profit. Try to fit as many items as possible. So your constraint may be just they need to fit in the ship. You cannot exceed the storage capacity of the ship. But now here you're trying to maximize the items that you put. So in general optimization problems, this optimization function is given by the problem domain. So sometimes it may be minimization, sometimes it may be maximization. But in our problem, in the casting problem, the optimization really, I mean, any direction satisfies us, but maybe we can say a pulling out direction, which is, for example, it may be something like that. If we want to have a pulling out direction in which the x coordinate is as small as possible and y coordinate is as large as possible. I mean, such a direction corresponds to almost vertical pulling out direction. So if you prefer, for example, vertical pulling out directions, there may be a way to, that's a good problem actually. How can we write the optimization function for such needs? So in addition to this pulling out, your boss tells you that if there are possible directions to pull out, pick the one which is more vertical, the most vertical one. So how can you have it in the optimization function? So it's like we are trying to maximize y and minimize x, but these are two objective functions. We need to put them together in one objective function. So what is the way to do it? For example, maximize x minus y or y minus x, right? If you, no, maybe absolute values, or actually we need to maximize y over x, right? Maximizing y over x is the one that we are looking for here. So if we want to do this, if you want to write it in a simple single function, maximize y over x is the one you're looking for, right? Is it but the problem with this function is it's not linear. So y over x is not a linear objective function. So you tell your boss, I cannot do it in a linear program. I may need to do some other techniques. There are quadratic programming and other like semi-definite. There are other optimization approaches other than linear programming to solve for different optimization functions like this. Or you can just forget about this minimizing x. You can just say maximize y, okay? And this is going to correspond to C1 is equal to 0, C2 is equal to 1 in this objective function. Okay, you can have such an objective function as well. Just out of all the solutions, pick the one which has the maximum y coordinate. This may be the one this is going to be most vertical. Not true, actually. You need to look at the x coordinate as well to find the. But this maybe if you don't know how to solve these y over x, maximize y over x type of optimization functions, you may need to resort to some simpler solutions like this. Now, such an objective function actually gives us a way to determine a vertex of this feasible region. So imagine our feasible region is always convex. And here, this objective function, actually this C1 and C2, defines a direction. The vector C1, C2 is a direction in this two-dimensional space. And maximizing C1, C2, for example, maximizing C1 plus x and C2, C1x plus C2y corresponds to finding the extreme point of this, for example, if this is my direction, C1, C2. And this is my convex plane. The maximizing function or minimize, it may be even minimize, is going to be the extreme point in this direction is going to be the point that maximizes this objective function. So in other words, this objective function is going to tell us which vertex I'm going to pick from this feasible region to maximize this objective function. Okay, so this is this C1, C2 gives you a direction in this space, and the extreme point of this feasible region in this direction is the point you are looking for. So we don't need to maintain the whole intersection region. All we need to maintain is this vertex Vi, which maximizes this equation. So this is. But we are going to see there are 4 possible cases. Now we are going to talk about 4 possible cases how this Vi can occur depending on the constraints, depending on the feasible region and the optimization direction. There are 4 cases. In the first case, your feasible region may be an empty set. Okay, there is no feasible, no such point. No, if your intersection of half planes is empty, it means no, the Vi does not exist. So if any time such a case happens, the intersection of these half planes is empty set, you report that no pulling out direction is possible. The solution is called infeasible. Okay, this is the term that is used for that is infeasible. So that's case 1. The other case 2 is if it's like this. If there is the feasible region, for example, let this be feasible region, and this is my optimization direction. In this case, the point in this direction of this feasible region is unique. Okay, so this is the case we are looking for when this feasible region is bounded and the optimization direction is showing downwards, and this vertex is a unique vertex of the feasible region. The other two cases are, what if your feasible region, the intersection of half planes, is unbounded? Let me now use the other board. So this may be your feasible region. As you can see, if this is your optimization direction, there is no point, extreme point in this direction. It goes to infinity, downwards. So in that case, all we have is the direction. I mean, in this direction, if you increase your, since all the points downwards here are going to be feasible, you can continue increasing, I mean, you can continue decreasing the y coordinates, and your objective function is going to increase. I mean, your objective function at the end, you can get a value of infinity in your objective function. You can maximize it as much as you want. So this is, in this case, the linear solution is unbounded, and the objective function can get arbitrarily large values. And the last case is when one of the edges of this feasible region is normal to our C1, C2 direction. Okay, so this is the, this region is the feasible region. And in that case, all the points on this line segment are extreme in this direction. Okay, I mean, in this direction, any point is going to give you the same objective function value. You can choose this one, it's going to turn out to be the same. The C1x, C1y is going to give you the same objective function value. If you choose this one, any point on this line is going to give you the same objective function value. And in such cases, again, you can say that to uniquely determine a vertex, either this one or this one, you can say, I choose the lexicographically smallest. I mean, I choose the one with the smaller x coordinate, for example. You can say that if there are multiple solutions exist, you can choose the smallest x coordinate solution, this case. Now, these are the four cases. And the algorithm I'm going to describe after the break is going to be assume that at each time there must be a unique such vertex, because the algorithms, the main thing that we keep track of in the algorithm is this vertex. Okay, we are not keeping track of any convex polygons or nothing, or regions. In the algorithm, we are going to start with a certain vertex, and we are going to keep track of this vertex. Either we are going to update it, or it's going to stay the same. And at the end, after we process all the half lines, the final vertex, the remaining vertex, is going to be the solution. Okay, so in order for the algorithm to work correctly, we need to get rid of these unbounded cases and this case. I mean, this case, we already got rid of this case. We can, by saying that if such a case happens, we can choose this one, the one lexicographically smaller one, as our unique vertex. So this one, and the infeasible, if it's infeasible, we say that there's no solution. If the vertex does not exist, we can exit the algorithm at that point. If at this one, and we can say we choose the smallest one, and the other case was the unique vertex. And the thing that remains is, if we have such an unbounded solution, how can we determine a unique vertex? And the way to solve it is just adding some imaginary lines that are very, for example, if it's in this direction, based on C1 and C2, if C1 and C2 are both positive, for example, we are going to, if they are both positive, if they are, for example, in this direction, we are going to add two lines that are very far away on the x-axis and that are very far away on the, so we are going to add these constraints. So x is smaller than this number, y is smaller than this large number. So we are going to introduce these large numbers and we are going to bound our solution. So this is going to be our initial vertex. So if no constraints are available, if imagine no half planes were there and you want to maximize C1x, C2y, if C1 and C2 are positive, this is going to be your extreme vertex initially. This is going to be your initial vertex V0, which maximizes this C1. I mean, it can be any direction. If C1 and C2, both of them are positive, this point here is going to be your extreme point that maximizes this function. So you are going to bound it, the unbounded cases like this. So after the break, we are going to see how what we need to do to update this vertex at each iteration.